quieted down, so maybe we should start. I mean, how did you know that the minute hand just hit 12? It's perfect timing. So I'm Phil Duffy. I'm one of the organizers of the Climate Change 101 series, and I'm going to very briefly, but guys can't hear me? Okay. I'm going to very briefly introduce today's speaker, who is Jay Lund from the Department of Civil and Environmental Engineering at UC Davis. Jay is, I would say, one of the world's experts on water resources management, and in particular on the problem he's going to talk about today, which is how do we manage and adapt the water system in California to anticipated changes in climate. And I think this is probably one of the most important, or the most important potential impact of climate change on our state is will there be enough water, or how do we make sure that there's enough water? So let me give you to Jay. It's a pleasure to hear you talking. I wasn't here 2 weeks ago because Jay and I were at a conference. I think you gave 8 talks there, Jay. Your students gave about 5 more. Yeah, well, right. So I'll be reminding Jay to shut up at around 12:45, so we all can go back to work. Okay.
You hear this okay? Okay. Thank you all for having me here. Thanks to Terry and Phil for inviting me. I'm really a water management person, not a climate change person, which in some ways befits my talk better than being a climate change person. So I want to talk about, well, what do you do when the weather changes? About climate change and how do we adapt our water management system in California. We've done a fair number of studies for this, and having a short attention span and not being very judicious about what to choose, I'm going to try to talk about all of them. So I'm going to try to talk very fast, and hopefully we'll see how far I get. I do a lot of large modeling work, large-scale water modeling work for the system of California. And anyone who knows much about large-scale modeling knows that a professor can never do that. He has to have students. And so the real work in all of this is done by these people, lots of students. Now, people that are doctors, and now they're professors on their own who have students who are doing their work for them too. So I have to thank all of those folks. As an overview of what I want to talk about today, I want to talk about climate changes because people often talk about climate change or global climate change like it's one monolithic thing, but it's not. It's a lot of different things, and I want to spend a little time going through how you can disentangle that maybe a little bit. We're going to talk about other changes as well, because in the next 50 or 100 years, climate's not the only thing that will change. The population will change, the land uses change. We don't have to look very far into the past to see how much change we've had in population, land use, social values, economy, technology. That stuff is still going to change into the future, and it's going to change along with climate. And then I want to look at adaptations in really 3 different areas: floods, droughts, sea level rise. And the focus is really going to be on the adaptation approaches, methods, what seems to work, what doesn't seem to work for different kinds of climate change, and what are the economic costs, because most of the modeling we do combines both engineering and economics. So let me begin with a little introduction of different forms of climate change. And I want to start with where I think there's the most consensus, and then I'll sort of move down to the more and more speculative forms. First, sea level rise. The sea level has been rising since the end of the last ice age, some 10,000 years ago. It will certainly continue to rise. There's a general notion that the rate of sea level rise is accelerating. So it is going to rise. We're not quite sure over how fast it will rise, but it's going to happen. Climate warming, there's almost as much consensus that the climate is warming as sea level is rising. Again, there's a lot of argument over what rate at which it's rising. And there's a lot of uncertainty, I should say, over whether it will be wetter warming or drier warming. Generally, in the thermodynamic sense, my thought is that on a global scale, you would expect it to be wetter as climate gets warmer. But locally, you don't really know. So the big question, as you'll see in some of the results, is this warming going to be wetter or drier? Then we have all kinds of other climate changes. We have climate oscillations. The El Nino, the Pacific Decadal oscillations, the Atlantic oscillations, things like that. Various multi-decadal droughts. One of the results I'll present comes from a very nice study that was done of looking at a drought that occurred around 900 AD or 1200 AD that lasted for 150 years. That's a climate change. It might be a long drought or it might be climate change. Certainly in the span of our careers, we'd see that as a climate change. And there'll be other forms of climate change. We haven't really started to study climate change in a serious way, but only for a few decades. And so we'll be finding some more, don't worry. Sort of a last perspective, there's really only one way that the climate can change the same. But there's many ways that it can change. And so when someone says, have you looked at this with respect to climate change? To me, it kind of just begs the question, what do you really mean by that? Do you want to see how it performs with a wetter climate, a drier climate, sea level rise, different degrees of warming? It's sort of a vague question. It's like saying something is nonlinear. Okay, well, I know what linear means, but what does nonlinear mean? Can you be more precise? And sometimes to do analysis, you have to be precise to be useful. So we make the mistakes of being precise when we do computer modeling, but it's the only way you can do it. So some of the other big changes that are going to happen in population growth. This is a map of land use that was derived by John Landis and his group at UC Berkeley for the year with 92 million people, say roughly in the year 2100. So you can see the greater Bakersfield, Sacramento metropolitan area and the greater Colorado River, Ventura metropolitan area. This is for 92 million people. Today we have maybe 40 million people. 2 or 3 times the present population. And so along with these big future changes in population, we're going to have big changes in land use, social values. Certainly our value of environmental uses has changed tremendously in the last 50 years. We can expect to see changes in the future. Economic well-being, crop prices, yield, et cetera, all kinds of things will be along with climate. So in adaptation, so for me, a water management kind of guy, you got to manage all these changes together. Whatever mix of climate changes are superimposed on each other that nature and the anthropogenic changes throw at you, as well as all the other changes in water demand, technologies, and things like that. And in some ways, this is not new. If you want to look at an example of really abrupt and severe climate change, you only have to go back and look at the early settlers to California, early North American settlers to California. But consider the Donner Party might be an extreme example, but they were coming from a place where they were used to having humid, wet summers, right? Where irrigation water was provided you out of the sky for free. They came to California abruptly. They had to change the way they did farming, the way they organized themselves to do agriculture, the way they organized their public works. Very abrupt, severe climate change, along with all the other changes that they were experiencing. It took them probably 50 years to figure it out. So it's going to take us a while to figure out how we're going to adapt to all these changes as well. But fortunately, as a relatively mature society in California, we have a lot of adaptations available, and some of those you'll see are in the little studies. So I've got about 4 studies here that I'll try to whip through. First of which, the first is on flooding on the Lower American River. So you all know where the American River is? Up there someplace, I think. Sometimes they've had floods there, or sometimes they've almost had big floods there, or here even. And so what we want to look at is, this is a little study of global warming or climate warming locally, levees, and urbanization. These are sort of 3 scenarios we're going to look at for future climate. And we're going to look out about 150 years. So here is the mean annual flood peak. So what we have is a probability distribution of floods. It's got a pretty long tail. What we're going to do is we're going to look at what happens if you shift that distribution over time along with these 3 scenarios. So the stationary hydrology is going to take that current probability distribution of floods. We'll keep it the same out for 150 years. And then we'll take what's a historical trend that people have noticed after the 1986 floods, and we'll project that out for another 150 years, shifting that probability distribution to worse floods. And then we're going to go really extreme and take a very wet form of climate warming, the HCM2 regression model, or HCM model, and that's really going to make it much worse floods. What we want to do is see what does this imply for management of the levees on the Lower American River system. So we're going to go out 150 years, and we're going to look at we have a computer model that optimizes in a very rigorous way the optimal heights and setbacks of the Lower American River levees for the next 150 years. So at any point in time, you can raise the levees and you can increase the setback of the levees at some often very large cost. So with costs in there. What we're going to try to do with this model is minimize the sum of the average flood damage, levee construction, and lost urban and floodplain land value. So if you move the levees back from the river, you've lost some urban land that has some value. Move the levees closer in, you gain some urban land that has some value. You raise the levees or increase the setbacks to increase the channel capacity to reduce the probability you're going to have floods. But you've paid some more, and maybe a lot, in terms of levee construction. And throughout this 150-year period, we're going to be changing the flood probabilities, as we saw, by shifting that probability distribution of floods out. And we're also going to be changing a couple of other things, the urban land and flood damage values, because as the Natomas area settles, it has more people there, it has more things you want to protect. There's more damage if it floods. So just like you will insure the shack out behind your house for less than your house, that land value and that property value becomes important. More people live there, you might want to protect it more, even if the climate's not changing. So this is with urban growth alone. So here we have increases in urbanization, urban land values, if you will, Natomas area by 0, so like today, and then we increase it by 2% per year and by 4% per year. And we've got the optimization results shows the optimal levee heights here. These are pretty approximate. These are meters, by the way. And then up here is the levee setback. So what you see is over time, you want to make the levees get higher as the land that you're protecting becomes more and more valuable, or more urbanized, more people there, more damage. Notice up here, though, in the levee setback, that as that land becomes more valuable, so does that floodplain land. Just the numbers on the economics. There's a lot of other things you'd want to consider in terms of environmental value. Just the numbers on the economics. So if you had urbanization alone, over time, you'd want to continue increasing the height of the levee. So once you've paid off all the bonds for the current levee improvements, well, coming decades, there's going to be more of them. There should be more of them, in all likelihood. I wouldn't believe these numbers exactly, but I would believe the trend. Now, let's look at it with a slightly worsening rate of flood damages. So we're going to look at that historical rate of flood frequencies getting worse with no increase in urbanization, 2% per year increase in urbanization, and 4% per year increases in urban land value. And you can see, again, it wants to raise the heights of those levees, but it never does want to change the location of those levees for 150 years. But notice the top of this. What I did here was I capped it out. I didn't allow the levees to get higher than 20 meters. 20 meters is 60 foot. How 60-foot levee? Would you want to be behind a levee that was taller than 60 foot? So that's why we capped it out. It just seemed unrealistic. If left to its own devices, this just keeps going up. Stop there. Now let's look at these different rates of urban growth with this very extreme, very wet form of climate warming. And you can see here, there's a major construction project going on for the next 100 years on levees. And then out here, after it's capped out for a while at 20 meters, you start moving the setbacks, increasing the setbacks out about at year 100 or so. Maury Roos will still be here, but most of the rest of us won't be. I think this is really amazing. This just gives you a sense for that 2% urbanization with the extreme climate change, where those costs come from. So here you see this red cost is the average flood damage. So it increases until you move the levees back, and then it increases again at 2% per year. We have some foregone land values that increase once you increase the setbacks. Then the black line is the construction cost, so you can see the little increases in levy costs, and then a huge cost when we move the setbacks. $1 billion or something like that. And then this looks at this in terms of more traditional terms, in terms of channel capacity, flood control channel capacity on the Lower American River. That's the blue line. You can see as you increase the heights of the levees and you increase the setbacks, you increase the channel capacity. And then here's the flood frequency that channel capacity guards against. Remember, that flood frequency is changing over time as the mean of that probability distribution of floods gets worse and worse. That's in black. So you can see as you build the levees, it gets better, and then but as that land value, as that probability distribution of floods gets worse and worse, then it gets worse. One thing I want to notice here is we often talk about shooting for the 100-year, or maybe if we really stretch, going for the 200-year flood protection for our urban areas. What the model says is maybe you ought to be looking for 500-year flood. The Dutch, by the way, for their cities, they protect it to the 1,000-year or the 10,000-year event. We're just pikers here, not really serious about flood control. So some observations on the flood control side for the Lower American River. Climate changes and urbanization alone can be accommodated by raising levees, but when you add these things together, it's much more likely that you will want to raise levees and increase setbacks, even though you have tremendous costs for moving levee setbacks in an urbanized area. And then, final point, flood control. This idea of 100-year flood planning is kind of a bad wager. It's really poor economics. It's a bad business decision. So that's the flood control side with levees. Now let's look at water supply with climate warming. And most of the results here are for the year 2100, but some of the results are for year 2050 populations. And we're having different climate warming scenarios, both wetter and drier, along with changes in population, land use, and accompanying water demand. So just as sort of a summary of climate warming and what it does to water supply in the state of California, this is a plot of total inflows of surface water into the Central Valley over the course of a year. It's this thick black line is what we have today. So you can see the winter, then you see the snowmelt bulge, the snowmelt tails off, and then it starts to rain again. These are 12 different climate warming scenarios. So when someone says climate change or climate warming, they still haven't told you a whole lot. There's still a lot of different ways this can occur. So we have relatively wet forms of climate warming, very dry forms of climate warming, and all kinds of things in between. But you'll notice a general reduction in the flows in the springtime and a general increase in the flows during the wintertime. The summer, just a little bit less. Although sometimes just a little bit more, but usually a little bit less. You don't have that snow melt. And we want to look in particular at two models of PCM and HCM. This is the same HCM as very wet previous study. Compare that with the historical hydrology. Here's the average availability in terms of millions of acre feet per year flowing into the Central Valley. So we have a dry warming, and wet warming a little bit. So what could we do if this climate is changing? It's getting warmer and there's more or less water. What can we change? A bunch of things. We can change the operation of all the dams, reservoirs, and the groundwater pumping, things like that. We can maybe coordinate the operation of some of those facilities, both groundwater and surface water. We can change our water allocation. Maybe with a new climate, there's some water uses that you don't want to continue, others that you might want to invest in more. So we have different water allocation, water markets. means of doing that. Urban water conservation and use efficiencies, they're very popular, and with a growing population, they might become more important. Agricultural water use efficiencies and fallowing. If you're going to, certainly if you're going to buy water from agriculture and put it into urban areas or something like that, or from low-valued agriculture to high-valued agriculture, you might see some fallowing or some agricultural use efficiencies in the selling sectors. Environmental water use efficiency. You might find that there are better ways of providing for salmon, just throwing water at them. We might want to be more targeted in when and where and how we water to them and accompany it with riparian habitat. And then in the future, we certainly, and even in the present, we have these new technologies of wastewater reuse and seawater desalination. When do these become useful? How bad does climate change have to be before we see these? California really has a very rich mix of options available for water management, particularly on the water supply side. And if you look at what water utilities are doing now, they're using a whole bunch of these things at once. So what we're really looking at is how do we orchestrate a whole bunch of different things so they match well together for the kinds of climate and the kinds of water demands and the infrastructure and the kinds of environmental objectives that we want. So a big problem, a big list of objectives requires a big model. And so here's sort of a schematic for California water system and the computer model we're using. This model has 51 surface water reservoirs, 28 great big groundwater basins, huge bunches of connections. You can see how highly intertied, how highly interconnected this system is. It covers about 90% of the irrigated acreage and about 90% of the population. So it's really about the only statewide model. We call this model Calvin. It has sort of two faces to it. It has sort of the mischievous 5-year-old Calvin, and it also has sort of the strict religious reformer. Because from the university, we're in a position we can do interesting things, sort of the mischievous 5-year-old, but also at the university we're trying to set a little more rigor to how we analyze and organize our analysis of big systems. So this model, it takes what we know, or some representation of what we know, for the surface and groundwater hydrology, water availability in the state. That might include some climate change scenarios. Our understanding of the facilities and the capacities in the system, the environmental flow constraints that we currently have in the system or that we might want to examine for the system. There are economic values for water deliveries, agricultural water deliveries, operating costs, hydropower, things like that. We have all of that information. We put that into a database, which feeds into some optimization software that was developed by the Army Corps of Engineers. And then out of that, we get the economic benefits, some ideas of operation of conjunctive use and operations, the economics of how valuable is water at each location in the system under various different conditions, and a lot of other really interesting things, including the value of increasing capacities. Also, the economic costs of environmental water flows. Those of you that like the technical stuff, we have Lagrange multipliers or shadow values for all constraints. But what this model really is it's a combination of an economic model, because we have the values of all these things, and an engineering model because we have the infrastructure and the operation of all these things. So it gives us a lot more economic insight into the engineering decisions, options that we have available. And it has most of those adaptation options that we had listed before. Again, it optimizes for statewide economic benefit for agriculture, urban, hydropower, and operating costs, but within the environmental flows that we mandate for the whole system. So essentially, as one person observed some time ago, this model gives the environment its water first. The rest is operated for economic purposes. So this is the results for 2,100 water deliveries and water scarcities for 3 different climate scenarios: the historic climate, dry, warm climate, driest of the 12 that we saw there, and the wettest of the 12 that we saw. This is for the north, central, southern, and then statewide. So north is the Sacramento Valley, central is San Joaquin Valley and Tulare Basin, and then south is south of Tehachapi, including the Colorado River area. So you can see with this dry warming, Sacramento Valley has a big shortage. San Joaquin and Tulare Basin have a bit of a shortage. South has a shortage no matter what you do, because there the farmers are selling water as much as they can to the urban areas, which have grown quite a lot by the year 2100. And then statewide, you can sort of see summing up of it. Light on this, the urban water deliveries and water scarcities. The urban guys do pretty well everywhere except for Southern California, where they just physically, you can't get enough water into Southern California because the pipelines aren't big enough. Otherwise, they would take more from here. Kind of interesting. But the state doesn't blow up and dry up and blow away. In terms of the cost, so we have the economic cost of this, not just the millions of acre foot of deliveries. You can see the urban guys, they are hurt a little bit. This is a base case if you were to stay with the current operations as of about 10 years ago. Have a big cost here, but for the urban guys, you see a little bit of increase in costs to them, water scarcity costs to them. But really, you can see that agricultural hit with the dry climate. So what you see is the junior water right holders in the agricultural sector, they're just without water. They're left high and dry. The senior water right holders, they often will be selling water to the growing urban areas. So they'll be fine financially, but their communities will, well, they'll be a lot sparser. They'll be moving to urban areas. The adaptive responses that come out of the model results, we see a lot more groundwater storage and conjunctive use because you're trying to get every drop that you can of the water that's left. A lot of water market transfers, agricultural to urban, agriculture to agriculture, particularly agriculture to urban in the Colorado River and the Central Valley. Quite a number of water quality exchanges, save people money, and a lot of flexible trading from year to year, having these trades vary. We see a lot of wastewater reuse. The cost we had here was $1,000 an acre foot. That price, we see quite a lot being done. For seawater desalination, we saw a little bit of that being done, but not more than about 100,000 acre feet a year, because the cost we had for that, it was $1,400 an acre foot, which is about what it is now. And then we see a fair bit of urban water conservation and use efficiencies. Essentially, what we're seeing is this portfolio, this mix of things being done to respond to changes in climate and the change in population. I mentioned the economics before. This is what we see from the model in terms of the value of expanding facilities. Talk about water bonds and peripheral canals and things like that. So now we're going to go out way into the future. We've got a lot more people. We've got a worse climate in terms of the dry-warm hydrology. What's it worth to expand stuff? So we tried to take the most valuable surface water reservoirs and some of the most valuable conveyance expansions and get numbers for them in terms of their average value. You can see that when we go from the historical hydrology to the dry hydrology, threefold, maybe a threefold increase in the value of expanding those facilities, but really the value of expanding facilities. If you want to invest in facilities, invest in conveyance. As a business decision, that's the place to go. Point of that slide. Of course, if it's wetter, then it's not worth as much. So. Environmental flows. Okay, gosh, let's dry the place out and see what these environmental flows are costing the economic sector, other human use sector. And you can see these increase as it dries, sometimes a factor of 10-fold, or maybe 30-fold, or 20-fold, something like that. So that's really hard. Here again, then if it gets wetter, these current costs of environmental flows, they go down. Notice here with dry-warm, the delta goes up a whole bunch. You have the dry-warm climate, it becomes very important to make sure the delta works. If the delta is broken and you have this warming, then you're in big economic doom. That's what I'm saying on the internet. I'll skip this slide, but we use more conjunctive use. In terms of storage, in terms of the operation of the reservoir system, when you have a warmer climate, you see the reservoirs fill about a month or so earlier. This is a graph that shows how the water is distributed among different reservoirs, because we really need to operate this whole system as a system. Not your reservoir there and my reservoir here, but some benefits from operating it conjunctively in many cases. And this shows that the way that you distribute and operate the reservoirs might change as the climate changes. So you have to have some way for these reservoir operators, who are often owned by different groups, can get along and negotiate how to reoperate the system. So some observations from this very extreme uh, year 2100 warming scenario. Future water demands matter too, not just the climate. Uh, and even with this kind of extreme change, California's system can adapt, but it's at some cost. It's at a couple of billion, $1.5 to $2 billion a year cost. $1.5 to $2 billion a year. That's a lot of money to you and me. I would like to have just like 1% of that, But California today has a $1.5 trillion economy. So it's a lot of money, but it's not the life or death of California. This Chicken Little, needn't be in the conversation. We see a lot more expanded use of groundwater to dampen out the variability with drier conditions. And we see in the model results a lot of groundwater taking our drought storage that we currently maintain in surface water and moving it to groundwater. Now, that costs you more in terms of groundwater pumping to get it out during the droughts, but it does make water storage capacity available relatively inexpensively to capture that greater seasonal variability in inflows with warming. And then drier conditions make the delta much more important. Now let's go. You thought that one was bad. Year 2100 climate warming. Now let's go look at the great drought of 900 AD in the year 2020. So we're going to take this Paleo-drought that occurred about 900 AD, where there was between 40 and 60% of the mean annual flow, historical mean annual flow. And we're going to take the most pessimistic view of that. We're going to say we're going to develop a hydrology that has 40% of the mean annual flow, and we're going to run it through the same model with the year 2020 population. We'll see, does California blow away? We know this drought existed because of some paleo record in the size, seeing tree stumps that are now probably underwater around Mono Lake and that lived for a long time. You can count the tree rings and you can carbon date the pieces of wood. And you see these signs of this drought elsewhere in the Sierras. Scott Stein did a lot of wonderful work on this. Talked with Scott in developing this hydrology. Well, we run that through the model, and you can see the scarcities, particularly for agriculture in the Sacramento Valley, San Joaquin Valley, California. A little bit of urban scarcity in Southern California, but mostly it's agricultural scarcity. And it's not as bad as you'd think. You'd think if you took away 60% of the water from the state, you think, well, maybe that takes away 60% of the water from agriculture. But no, because this particular drought is all dry years, taking away a lot of the wet year water that would spill. As we used to say, flowed unused to the sea, right? Well, that's all gone in this drought. And so actually the impacts of that drought are not as bad as you would think, but they're still not good. In terms of groundwater levels, I think this is kind of interesting. Now we have a drought that lasts for 150 years. Well, here we modeled only the first 72 years of it. And the groundwater just stays low. It doesn't vary as much as when we optimize it with historical hydrology or what we have seen in the historic operations. Surface water also stays low all the time. Every year is a drought, so there's no wet years to refill it. So if you were to build an extra big reservoir, and then this drought hits, does it provide you much water? Probably not. Something to think about. Doesn't fill. Observations on this super drought, we call it. California's water supply system can adapt to a severe prolonged drought. It's very costly, but again, it's not catastrophic. So 95% of the economy is the urban economy, and it's still relatively well watered. Not highly watered, but not drying up and blown away. Severe regional and economic and water supply impacts for agriculture. So it's not severe for the state economy as a whole, but if you're a localized region or a local town that's rural, it's darn severe. And then this lessened hydrologic variability that you get with this particular form of climate change means it doesn't really care about groundwater and surface water storage anymore because it's dry all the time. Storage isn't surviving. Okay, so the last little vignette, I got to fit these in a minute here. Last one is sea level rise in the delta. This is the thing we're working on mostly these days. I'll have another report coming out in a few months, I hope. The problem here is with sea level rise. This is the most certain of those forms of climate change. And increasing island failures with problems with seawater intrusion, island failures, and drinking and agricultural water supply quality and availability, I suppose, from that perspective. And our options for dealing with are either reducing exports, increasing delta outflows to keep that salt at bay, or keep that salt out to sea, or building some kind of a peripheral conveyance, isolated facility, circuitous conveyance. And so the question is, how would users adapt? So we took this big Kelvin model again, and we looked at that. So this is just another slide of the delta. This is the huge amount of subsidence that's in the middle of that former wetland. Why it's becoming less and less stable. But how many of you took fluid mechanics? Well, if you have water level down here and a land level down here and a water level up here, the sea level is rising and the land is subsiding, what's the equilibrium condition of that system? Okay, so we know the equilibrium condition. Those of you who took chemistry, we know the equilibrium condition of this reaction. We just don't know the kinetics. EPA building, I figure somewhere here, I don't know chemistry. So now we ran this Kelvin model a bunch with different levels of delta outflow and different levels of pumping capacity. So we restricted exports to the rest of the state, to the southern part of the state, and we ran it without restricting the exports to the southern part of the state, except for the physical conveyance capacities. But we did increase the amount of delta outflow that we required in order to keep the salt out. You can see how these diverge. At the beginning, it doesn't really matter. But after a while, it really does matter. If you end exports, that gives you about 18 million acre-feet per year of annual outflow to the sea, which is at a cost of about $800 million a year more than if you didn't end exports, but if you just required those flows to go out to the sea, and you allowed that extra flow to the sea to come from both reduced exports and from buying water from lower valued purposes throughout the state. $800 million a year of potential profit for someone. You know somebody's going to sell that kind of difference. So this is an important strategic point, I think, for how we manage the delta. If our problem is increasing exports, how you do it is important economically. It certainly has local implications, but these are the statewide numbers. And if you're interested in ending exports, that might not be the efficient way to get outflows increased. But if your problem is that you think the pumping is sucking up the little fish, then maybe that's what you have to do rather than an outflow. This just shows how, as you increase required delta outflows or end exports, NE is no exports. Different agricultural areas in the San Joaquin and Tulare Basin are affected differently depending upon where they get most of their water from. Sure. Okay. Right. This model only looks at the water delivery and water cost implications to the rest of the state. Separate, so you have to do the economics within the delta separate, I think, in our current technology from looking at the implications of that for the rest of the state. So this model really is good for looking at the implications for the rest of the state. We have another group, actually, who's looking at the economics within the delta. We don't have results for that yet. So in terms of sea level rise observations, the delta is really the water system's weak link. Ending exports is very expensive. Economic losses increase with delta outflow, and flexibility in trades greatly reduce the costs of increasing outflow. So let me sort of start to sum up now. Challenges for the future. We've got a lot of major challenges however the climate changes. No matter what form of climate change, nature and anthropogenic changes throw at us, we're gonna have to deal with them, and they're going to be major challenges. Any of these scenarios, even the milder ones, just with the population changes and such, are pretty challenging to us. I haven't even mentioned the Endangered Species Act, did I even? So, gosh, we're no end of fun in this field. Flexibility is valuable. You have a rigid system. Everybody negotiated 50 years ago about how they wanted to deal with the system. Take that negotiated solution and you project it 50 or 100 years further out, like we're doing now in many cases. You're not going to be near the optimal solution. It doesn't take a PhD to realize that. I'm sorry. There's some major regulatory challenges in this. What we've seen in the Delta in particular is an accretion of regulations and institutions to keep the Delta as it has been into a situation where it is increasingly unable to do that. It'll be a big challenge for us, along with the institutional aspects, all the operating rule agreements, the cost allocations, things like that for the system, land and water management. So it's not just water management in many of these cases. The Delta is almost as much about, maybe more in some ways, about land management than about water management. Same with flood control. Where you put the people is where the damages are potentially going to be. The state has benefited tremendously by keeping people out of the bypass system. That was essentially, we decided to dedicate that amount of land to a flood bypass system. We get agricultural uses out of it. Maybe in the future we'll get more habitat uses out of it. But we kept the people out of it, and it saved us all a wealth of money. Something to think about into the future. It was very hard for people to do that then. It's not going to be any easier now, but it's probably just as important. And then sort of my final point, sort of methodologically, we've really only begun to understand California water management using numbers. We have a lot of very smart people who work on this system who know a lot about the system, but it's very hard to organize and run and investigate such a very vast, complex system if you don't use numbers. Not precise enough in that. So as a professor, of course, I have to advocate using models and numbers because I think they help us work, design, build, develop policy for water systems, just like it helps make our airplanes fly and our buildings stay up. You wouldn't want to live in a building this big that wasn't designed with a computer these days. It wasn't designed with numbers. Well, that's my last point, I think. Oh, here's some citations. You can find these on my website, the papers for each of these studies. And then questions. Oh, this doesn't show up so well. This is really developed for the Delta, but it works, I think, just as well for climate change in California water. It's sort of a Dutch theme here, because the Dutch sort of live in our same kind of world where water is important. So these are Bruegel, Tower of Babel. We have all these different tribes, interests in water that all speak in different languages. Hard for them to understand each other. And then sort of the blind leading the blind. Bruegel, little Dutch boy trying to keep those levees in the Delta going. And this is a real levee. This is a Dutch North Sea levee. With my father down there. It's, that's the 10,000-year event. Thank you very much. The question was, what are the highest functioning levees in the world? I don't know. I haven't been to visit them all. If there's money to do that, I'm happy to take advantage of it. I just sort of had in the back of my mind that that's the biggest levee I'd ever seen. That can't be much more than 20 meters. It's a round number. That's a question in the back. Sure, we had the 86 flood just a couple of years before we had the drought of record, much of the state. Well, the Calvin model is primarily a water supply model. It has the flood control pools and stuff, so it's really just the water supply. Yes. Yeah. Oh, yeah. So the question was that electricity prices remain stable in the models. That's true. I don't know. I'm not a hydrologist. That would be a question for Phil. I just do the management. To me, that's one of the interesting aspects of this whole problem of climate change. How long did it take us to figure out what the climate was last decade? It took, as a society, it took us about 100 years. And after the 86 flood, we decided, oh, maybe the flood frequencies are worse than we had thought when we built the dam. So we're going to be sort of chasing our tails on this for 50, 100 years. You have to have water if you're going to have reservoir work. Hmm. Right? Sure. You make your bets and you take your chances. You just try to think about it. I mean, how do you decide what stock to invest in? There is inherent uncertainty in this world. Yes, because he noticed that in the 2100 study that in terms of statewide water scarcity, there wasn't a big difference between the historic hydrology and the wetter climate, and that's because you don't by the year 2100 you're you don't need that much more water. It's only a couple $100 million improvement in the statewide economics for the water supply side with the wet warm climate compared to the historic climate. But it's like if you had an extra garage on your house, room for an extra car, would the benefit of having that extra garage be more than the cost to you of taking away one of the car spaces in your garage now? So usually the more you get, the less valuable it is. But if they start taking stuff away from you, you really notice it. That's essentially what you're seeing. Plus, the wet is not as wet. The wet is not as much wetter as the dry is drier. About twice as dry as it is wet. That's correct. That is correct. Oh, that's a wonderful question. I'm glad you asked that. so, the observation is, even if you had, I'm going to paraphrase your question a little bit. Even if you had the same amount of runoff but it was with a warmer climate, you would expect to see less spring flow and more winter flow. Wouldn't that mean that you wouldn't be able to capture all that water? Okay, so if you look at many of the tributaries in the state of California, many of the major water supply reservoirs, one of my favorite will be the Tuolumne. The big reservoir there is New Don Pedro, has a capacity of 2 million acre feet. There are three major upstream reservoirs that have another additional capacity of about 600,000 acre feet. So combined, just on that one basin, you've got 2.6 million acre foot of storage. The mean annual flow on that river, I think, is 1.7 million acre feet. So if those reservoirs started off empty, so if you took the drought storage and you put it underground someplace else, which the model kind of likes to do, then it doesn't matter what season or what day that water comes down the river. You can still catch it. Have it a big enough bucket at the bottom to catch the annual runoff. So that explains, I think, and you see this quite common across the system, why the system is actually able to handle the shift in the runoff pretty well for water supply purposes. On the flood control side, while the models show that for the wetter, dry, warm climate, it's okay, on the flood control side, those extreme events, those years that you get maybe 5 million acre feet coming down that river instead of 1.7, then you couldn't catch it, and you would have major flood control problems, I think. That's what the first study said, I think. Well, our model has the environmental flows in it as well. You know, there are some interesting problems. Sure. My favorite quote on models is by George Box, that all models are wrong, but some are useful. Right? You know, just like when you do calculations for your retirement planning, right? You believe those numbers are wrong, right? I hope, but you still find them useful. No, they're not here. Oh yeah. I didn't mean to leave you the impression that everyone is going to be happy in this world. I'm sorry. That's another one of my favorite questions. You know, so to try to paraphrase and maybe repeat the question, if you improved agricultural water use efficiency, would you be much better off? Why wouldn't we do that? Okay, so let's say you're in the Central Valley and you apply, say, 3 foot of water to your field, and the crop evaporation is maybe 1.5 foot. Apply 3, so that's a 50% efficiency in a sense. What happens to that other 1.5 foot of water? It goes back in the river, and then they pump it out down to LA. So it's really not lost. And so for most of the Central Valley, the agricultural water use efficiency is not a very good indicator, because that efficiency is a localized one. You account for the return flows that can be used downstream, the efficiency is actually much higher in a statewide sense. Now, if you're down at the Salton Sea, by the Salton Sea, and you're looking at irrigation efficiency for Imperial Irrigation District, that extra water that they would apply there that flows into the Salton Sea, that's not available for reuse. So that is the local efficiency there is the statewide. That water is no longer useful. whereas for the Central Valley, most of that water is. There are actually a few places, I think, in Central Valley where my understanding is that they seek to have inefficient agricultural use deliveries in a narrow sense because it increases the groundwater recharge. Well, that's a good question. You might see greater evaporation from that extra 1.5 foot with the warmer climate. Sure. Yeah. You obviously want us to do this, so no, I don't disagree, but that's just another layer of numbers. Mhm. That makes sense to me. I think for the long, well, yeah, right. That might be the long term for many people. Mhm. I, I don't, I don't think so. I feel more comfortable at 500 year, wouldn't you? but in my, our numbers, which I would have to say are preliminary, because you know our studies are, we do the $80,000 a year study, not the study that you do if you're really protecting billions of dollars worth of assets. The model that we did. Yeah, we had some very high costs for moving the setbacks. I think they were like 30 or 50 or maybe 80 meters. They're a substantial setback. Right behind you. Yes, it is. Well, they probably don't understand global warming any more than you or I do. Maybe even more than Phil does. He probably knows about it more than I do. It's just hard to understand at this point. Uh, you do see occasions where the water operators do talk with each other and they do cooperate. They have found efficiencies and benefits from working with each other. Particularly, I think, since the last big drought. Droughts are always good for getting people to cooperate as well as fight. But I think I'm actually pretty optimistic. With the advent of water markets in the last decade or so, it's a lot easier to give people incentive to cooperate. Sure.
I've actually been pleasantly surprised at the degree of technical sophistication in some of the larger water agencies. Certainly, a lot of them have uh, people like Jay and I, PhD level people who are very technically sophisticated. That's not the smaller agencies can't afford that. But a lot of the water agencies are I would say hipper than you might.
Yeah, actually, California is very much blessed with having a lot of very smart people work on it. That's one of the reasons why it's so much fun to work on this system. Is there's a lot of very smart people who've spent a lot of years working on this system. Right. 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 Mm-hmm. 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 Right. Well, I don't think it'll be out. We took this extreme 2100 with this huge population increase. About half of the increase in water use for urban areas came from reduced agricultural water deliveries because of the urbanization of agricultural land. So that actually makes it a little bit easier. But still, you had about half of the water use was still agricultural. So it tended to be higher value. So when I talked with my colleague Richard Howitt, who's chair of agricultural economics at UC Davis, my understanding from talking with him is that California is still going to have a huge, relatively large agricultural economy. It'll still be about 5% of the state, but state economy. But it's going to be more of the high value stuff that California has a comparative advantage in, and less of the commodity. I think so, but it's easy as you drive along to think that a lawful lot of agricultural land is being urbanized, because as you're driving along, what are you seeing? You're seeing that agricultural land that has the greatest accessibility to the transportation system. But there's a whole bunch of agricultural land that's far from that road, isn't going to be changing. I can't imagine. So I think there is something to what you say, but I don't think you'll still see a very substantial amount of agriculture in California. I think forever, even with these big droughts. Right? Still a lot of agricultural water delivery. Oh, yes. Right. Mm-hmm. I think it's really hard. We're not going to know what climate change is really going to be for us until after it's too late. Even for water right hearings, it will take longer than that. I mean, it's just an inherent problem. Thank you very much.